Hello, welcome to lecture number 3 over linear functions. We're going to start this lesson by looking at a graph of data points. So this graph could represent any sort of relationship. Each one of these points is individual events. So maybe this x-axis could be hours studied. So how many hours someone spends studying. And the y-axis could be how many points you improve on your test grade. Improvement. So each one of these points at 4, 5, after spending 4 hours studying, someone improved their test score by 5 points. After, let's say, 11 hours studying, one person improved by 5 points, but another person improved by 9 points. So this person probably studied better. Who knows? So we have an independent and dependent variable, and we've just got a whole bunch of different data points. What we're going to do is we're going to try and find a line of best fits, or a line that sort of fits these points the best. Let's first look at the points 8, 6 and 12, 7. So 8, 6, that is right here. And 12, 7. That's this point right here. And we're going to find a line that fits these 2 points. So what I'm going to do is I'm going to make a triangle. We're going to see how far we go up, how far we go over. Just find the slope. So from 6 right here to 7 right here, we go up by 1 unit. And then from 8 to 12, we go over 4 units. So our slope here would be 1 over 4. All right, so this is our slope. Now we need an equation for the line, and we can actually use the point slope formula to do this. We'll use this as x1 and y1. And if you wanted to do the formula as this right here to find the slope, you can do that as well. So we'll do y minus y1, so minus 6, equals m, or your slope, so 1/4, times x minus x1, so x minus 8. And this is our equation for the line. All right. And I don't like this being in point slope form. What I'm going to do is I'm going to put this into slope intercept form. I'll show you guys actually how to do this from here. If we want this in slope intercept form, all we have to do is solve for y. What we'll do is we'll distribute this 1/4. As crazy as this looks, we can distribute this 1/4 with the distributive property, just like any other number. This will give us y minus 6 over here. 1/4 times x is just 1/4 x. And 1/4 times 8 will be 2, and since it's minus, we'll have a negative 2 here. Now we just move the 6 over by adding it to the other side. And let me not cover up that problem. We are adding 6. Our final equation will be y equals 1/4 x plus 4. So negative 2 plus 6 is 4. That's our equation. So we should have a y-intercept right here, and this line will go straight through both of these points. So that's one line of best fit for this data, and it looks pretty good. It hits between a bunch of the points, an equal number above and below. Let's try a different set of points. Let's see if that works any better. 7, 5 and 14, 8. Let's use a different color so we don't get it mixed up with the points. 7, 5, 14, 8. 7, 5, 14, 8. Right, so we want to see how much we go up and how much we go over. I'm going to use the slope formula for this one instead of the graph. So in order to find my slope, this is 7, 5, 14, 8, same thing as written in the problem. We'll end up doing y2 minus y1 So this is x1, this is y1, this is x2, this is y2. So 8 minus 5 divided by 14 minus 7. That will give me 3 over 7. So this one has a different slope. It has a 3 over 7 slope, or a slope of 3 over 7. In order to get the equation, we're going to do the same thing. X1 and Y1, just plug those straight in. So Y minus 5 equals M, or 3 over 7, times X minus X1, or X minus 7. All right, and we're going to get this in slope-intercept form as well. Y minus 5, 3 over 7 times X is 3 over 7X. Three over 7 times negative 7 is just negative 3. All right, and then we're going to add this 5 over. And our final equation be y equals 3 over 7x. Let's see, erase some of this. Plus 2. And so our axis here is 2. Looks like we have a really similar line. Again, it goes through 2 of these points, and it seems to have a good amounts below and a good amounts above. So this is a good indicator of how many hours you would have to spend studying to get a certain points improvement. If you wanted to improve by 2 points, so 2 points, in this model, you'd have to use 0 hours of studying. In this model, it actually wouldn't even matter. Let's use a better example. Let's say you wanted to improve by 9 points. So in this model right here, you'd have to study for roughly 16 hours. In our original model, you'd have to study for, let's see, probably be somewhere way out here, so farther than 16, maybe 19 or 20 hours. So that'd be a little bit off the graph. So both of these equations are lines that fit the data set that we were given. And you can pick pretty much any 2 points, and they will give you a sort of a line of best fits, or a line that fits, but it won't be a line of best fit. In order to make a line of best fit, you actually use what's called linear regression, and that goes into statistics and upper level math classes. So actually that's defined here. Yeah, we won't be going over that in this course, but it is nice to know. So the main idea here is to be able to a line of best fits. Get your rate of change or your slope, plug it into point slope form, and turn it into slope intercept form. If you want to go straight to slope intercept form using some algebra ideas, you can absolutely do that as well. All right. Going over our previous formula, so slope is y2 minus y1 over x2 minus x1. Y2 and y1 in this case are defined by whatever you get when you plug in x2 and x1 into the function. Let's look at this example again. So right here, x2, y2. So in this first example, this line right here, when we plugged 8 into our function, we ended up getting, we ended up getting 6 as the output. So f of 8 equals 6. When we plugged 12 into the equation, so f of 12, we ended up getting 7 as the output. So f of 12 equals 7. And that's all this part is saying right here. So instead of calling it y2, they're saying, well, when you plug in x2, what do you get? And it's y2. This is just another way of writing it. All right, let's look at this example right here. So this is a polynomial, and we'll go over more of polynomials next week. So it goes up, down, and then up again, following this relatively strange looking curve. And it's given by this equation, x minus 1 times x minus 5 times x minus 7. We're being asked what is the rate of change on the interval from 2 to 8? This is going up in increments of 2, so 2, 4, 6, 8, 10. So 2 is right here, 8 is right here. If I look at this graph, it's actually kind of hard to figure out what f of 2 is. As maybe it's 12, maybe it's a little bit above, maybe it's 14, maybe it's 12 and a half. It's hard to tell exactly what it is. So what I'm going to do is if I want the rate of change from 2 to 8, it looks like it's increasing. Instead of just putting points on here and assuming it's going to be some value, I'm going to plug 2 into my function and see what it gives me. So f of 2 should be 2 minus 1 times 2 minus 5 times 2 minus 7. This just turns into 1 times 3, times negative 3. Times negative 5, which is just positive 15. So when I plug into that is not right. Negative. Oh, sorry, positive. Yes, that is right. So 2 is positive 15. So f of 2 equals 15. This is f of x1, if you would like to call it that. All right, so this is point number 1. Point number 2, now what I'm going to do in order to find the output for when I plug in 8, I'm going to plug in 8 into my function. So f of 8 will equal, everywhere I see an x, I'll just replace it with 8. So 8 minus 1 times 8 minus 5 times 8 minus 7. This will give us 7 times 3 times 1. This will just be 21. Okay, so when we plug in 8, we get out 21. So this value, I guess it'd be halfway in between. This value right here. So this point is at 2, 15. This point is at 8, 21. So we want to find the rate of change between these 2 points. So what's happening to the function if we're just looking at these 2 points, ignoring everything else? So in order to find this slope or rate of change, all I need to do is use my slope formula. So f of x2 minus f of x1, and I'll actually write out the entire thing in this format because we will be using this in the future. So f of x2 minus f of x1 over x2 minus x1. So when I plug in x2, or my second value, when I plug in 8s, I get out 21. So that's 21 minus f of x1. Well, when I plug in x1 or 2, I get 15. So minus 15. X2 minus x1, that's just 8 minus 2. And so this entire thing is the same thing as what we've been doing, just written in a different format. This will be 6 divided by 6. And that'll just be 1. So my rate of change is actually 1 in between those 2 points. So every unit we go to the right one, we go up 1. So we go 6 to the right, 6 up. Or 6 up and 6 to the right if you want to do that as well. All right, and that's my slope. Question number 4 is very similar, except you're not given a graph. You're just asked to do this right here. That'll be on your homework. I'll have y'all do that one on your own. All right. And so now let's look at a different way of solving this problem. This won't be entirely the most optimal way, but it will be very helpful for moving forward into an actual calculus class. So what we're going to do, I'm going to say 8 equals 2 plus 6. Well, where on earth did we get that from? If we look at the start of the problem, we're given this interval, 2, 8, from 2 to 8. So if I start out at this value of 2 and I add 6 units or go to the right 6, I get 8. We're just going to rewrite this second value of 8 as 2 plus 6. Right. So instead of x2 just being 8, we're going to write it as 2 plus 6. All right, what we end up with is something like this right here. And we're going to rewrite it in this format right here, and it's going to give us the exact same thing as this, but let's check it out. So f of 8, that's what we did for f of x2. F of 2, that's what we did for f of x1 over x2 minus x1. Yeah, same thing. All we're going to do right here is rewrite 8 as 6 plus 2, or 2 plus 6. And when we simplify this, this will just give us f of 6 plus 2 minus f of 2 divided by 6 plus 2 minus 2 is just 6. And it's the same exact thing we got right here. It's just the difference between these two values right here. And so this formula right here is a different way of writing this right here. And when you go into calculus, you'll look at sort of, instead of rate of change between 2 points, you'll have 2 points that get closer and closer and closer to each other. So maybe the point from 7 right here to 8, and we want to find the rate of change between these, or maybe 7 points, 5 and 8, and find the rate of change between these. Or maybe even 7.999 and 8, and find the rate of change between these. We'll try and get really, really close to finding the rate of change at just one singular point, or the instantaneous rate of change of a function. And when we do that, well, we don't have 2 points that we can plug into the regular slope formula. What we'll end up needing to do is looking at what's called limits. And limits work very, very well with this formula right here, rather than the original formula with 2 points. All right, so on the right-hand side, we don't have 8s, just 2. The distance between 2 and 8 is 6. Again, that is a part of the solution. This is our difference between 2 and 8. That's all it is. And again, we're just focused on the way this is written. So consider the general interval from x1 to x2. So instead of 2 and 8s, it could be any x values. So 7 and 8s, 4 and 10, whatever numbers you want to put. We can take this general formula right here, and instead of writing it like this, we can write it in this form called the difference quotient, or write it as a difference quotient. And so instead of writing x2, we know that x2 is your original x plus some value h. In this case, x2, or 8, was x1 plus 6. And we're just going to rewrite it like that. Instead of plus 6, it's plus h. So if we had x2 was 10, and we were looking at the output there, it would be x1 plus 8. Again, h could be any number, whatever the difference between your x2 and x1 is. All right, so we're going to say x2 is x1 plus h, and we're just going to plug that into this formula. And we're going to plug it in the same way right here. This one, it is being plugged into the original function, so we have to be careful. However, that's all we're doing. Instead of writing x2, we just write x1 plus whatever their difference is. That's what h is. H is the difference between x1 and x2. All right. And when we do that, we end up with this formula right here. And what we want to do is we want to sort of generalize it. Instead of, any 2 points, or any 1 points, x1 and x2, it could be any value x and f of x. So instead of x1, again, we can do this without misunderstandings. There's just one x coordinate being used here. So what we can do is, instead of writing x1, we can just write f of x. And it could be any value x. and it goes for any interval. And so what we're doing is making this a whole lot more vague or general, so it applies to every case. And in the future, we'll be looking at a limit. And don't worry about this too much for now. But as h approaches 0, or as the difference between x1 and x2 approaches 0, so as these two get closer and closer together, what's going to happen to this difference quotient? So again, the importance may not be too obvious now, but in the future, for actual calculus classes, this formula will be very, very helpful for finding what's called an instantaneous rate of change, just using one function or one coordinate instead of two. All right, so that was lots of abstract theory talk. Let's get into what you'll actually see on the homework. So this example says let f of x equals 1 over 8x plus 7. What is the difference quotient of this function? Our difference quotient is essentially just a slope at any given point. So let's try and find that. Difference quotient just follows that formula that we had above. F of x plus h minus f of x divided by h. And again, it doesn't just work for x1 being, 2, 3, 4, 5, 6. It works for every single x value. So if we want the difference quotient, well, first up, we need f of x plus h. So let's find that. Well, f of x plus h just means I plug in x plus h everywhere I see an x, or for all the inputs. So it will be 1 over 8 times in parentheses x plus h plus 7. Right, and we can simplify this a little bit. So again, we're going to distribute this 1 over 8. We don't know what h is. H is just the difference between 2 points. So 1 over 8 times x plus 1 over 8 times h plus 7. That is what f of x plus h equals. 1 over 8x plus 1 over 8h plus 7. F of x is just our original function. So again, the second piece of the equation we're trying to find is f of x. So f of x equals 1 over 8x plus 7. Nothing to simplify here, that's just a problem. Now if we want to find the difference quotient, again, h is an unknown, we can just plug in this for f of x plus h, this for f of x, and then try and simplify as much as we can. So what we'll do is f of x plus h, so that'll be 1 over 8x plus 1 over 8h plus 7. And then we'll do minus f of x, so minus 1 over 8x plus 7. I do have to be really careful with this minus sign. It's subtracting the entire thing. So I'm going to put it in a set of parentheses. And all divided by h. All right, so f of x is this blue function. F of x plus h is this green function, and we're just subtracting them. Now let's see what actually happens when I subtract these. When I'm subtracting something in parentheses, this negative distributes. We'll end up with 1 over 8x plus 1 over 8h plus 7 minus 1 over 8x minus 7 over h. All right. Well, 1 over 8x minus 1 over 8x, this cancels. 7 minus 7, this cancels. So just combining like terms, we've canceled a lot, actually. This works really, really nice. We have 1 over 8 times h divided by h. As crazy as this looks, you can, just doing some scratch work off to the side. If we have 7x over x, again, these two x's would cancel out and we're just left with 7. Same thing's going to happen here. 1 over 8 times h divided by h. These are going to cancel. This is just going to be 1 over 8. And actually, all the variables disappeared in this one. This is really, really nice. What this is saying is that any given points on the line, on the function 1 over 8x plus 7, has an instantaneous slope of 1 over 8, or has a difference quotient of 1 over 8. which I guess this is a linear equation, so it makes sense that the slope is the same the entire way through. Number 5 will be your homework. You'll have to find the difference quotients for these two functions right here.